I want to finish up talking about the whiteboards. Was anybody not here yesterday? Oh, yeah. So there's a discussion post, and I'm making it a grade, so go in and look at it and post something. So basically, I had you guys do whiteboarding on Tuesday of a energy diagram for a two-step reaction, with the second step being the slow step that was endothermic. And so we've been looking through some of the examples, and you guys wrote some comments on the different pictures, which were great. And I was just sharing some of the things that I saw, most of which you guys picked up on, or at least somebody picked up on. So this one was great. The only issue was that the activation energy line was drawn for the second step was drawn from the products rather than from the intermediate. And in that case, also, this probably needs to be a little bit taller so that it is still bigger than the first activation energy, because the slow step is always going to have the higher activation energy. And then this one also generally, lots of correct things here. Transition states labeled. Here, the activation energy again needs to come from the intermediate. In this case, not from the reactants, but it would be the right, size relative to the activation energy of the first transition state. And then generally speaking, I'll show you an example later where this isn't always the rule, depending on how people are drawing their energy diagrams. But generally speaking, and for all the reactions that you will be talking about in this class, the intermediate should be higher in potential energy than both the reactants and the products, because the idea is that it's a temporary state. It's not like two separate reactions. So if the intermediate was this much lower than the products, it doesn't make a whole lot of sense that you would then go from the intermediate to the products. It would take a whole lot of energy to get there. I mean, you can, but in the reactions that you guys will be studying in organic, the intermediate is going to be higher than both the reactants and the products. So that's kind of a minor thing here, but something to keep an eye on. And then this one, again, lots of good stuff. I liked the upward arrow for the delta H. If you're going to have a one directional arrow versus a two arrowheads just showing the distance, it needs to reflect the where that energy is going, which is it's going in. The activation energy here, again, needs to be from the reactants, and this one needs to be from the intermediate. So there's kind of, the EAs and the sizes of the humps need to be adjusted. But again, lots of good stuff in here. So again, if you weren't here, make sure you go in and write some comments on those diagrams. And now I want to get back into our study guide. We're going to talk briefly about this molecularity idea. And then we're going to get into talking about rate equations. And there's going to be a little blip here where I talk about why do we care. Okay. So this is page 5 in your HL study guide. And it's a very minor thing in terms of the curriculum. It's just in one page, and I hardly see any questions in the question bank about it. They could always ask you something. But it's a way of discussing, it's a way of describing a particular reaction or a particular step within a reaction. So whether we're talking about an elementary reaction where there's only one step, or we're talking about a step within a multi-step reaction, we can have something that's unimolecular, bimolecular, or termolecular. And unimolecular, it basically is how many reactant particles are there. Okay, so in a typical decomposition reaction, you're only going to have one reactant, and so it's going to be unimolecular. I'm going to show you that that's not always, it's always more complicated than that. But for our purposes, something that's bimolecular has 2 different reactants. Termolecular is going to have 3 different reactants. This isn't, we don't see this very often. And that's why, like in honors chem, we don't even give you any reactions where there are 3 reactants. And the reason is really because it's physically much more improbable that you're going to have 3 things collide together in the right orientation with the right amount of energy, which is what's required for via collision theory for a reaction to happen. So it's just a lot less likely. So you just see a lot less of that. So you can just look at the various examples. Both, hopefully you can see that both of these are going to be bimolecular because they have 2 different reactants. Okay. And what do chemists even do with this? Why do we care about it? I was looking some stuff up, and I found this paper that was published just last year. So this is not like back in the 60s we didn't know about this molecularity stuff. This is like current ongoing research. And I'm not expecting you to, read this abstract or anything. I will post the paper if anyone wants to look at it. But this is looking at reaction pathways for hydrogen peroxide with what they call hypochlorous species. And by hypochlorous species, we mean mostly what you would think of as bleach. And implications for wastewater reclamation. So how do we treat wastewater? They talk about this advanced oxidation technology. We'll be talking about oxidation in the future, using ultraviolet light and hydrogen peroxide integrated with bleach, essentially. And that is a way to treat wastewater. And they are concerned in this paper about exactly how are those reactions happening. And the premise of the paper, we think that we're using too much bleach. We don't need to use that much, and it ends up being less cost-effective and potentially less effective than what it could be if we were doing this. And of course, wastewater treatment is a very large-scale process. This is not happening in a flask. This is happening in gigantic holding tanks. So being more efficient about something, using less of our reactants, et cetera, is actually really important. And so they talk about how there are both experimental and theoretical approaches looking at whether this is a bimolecular or trimolecular reaction. And that has implications for the kinetics of the reaction and the amount of the reagents that you need. So I'm not going to go into any more detail with that. But it's a good example of a paper that, has a lot of stuff in it. There's slightly more advanced math than what we do, not super complicated, but you'll see if you look in the paper, you'll see some rate equations, like the ones we're going to talk about, but more sophisticated. And you'll see things like 2 different pathways and how they think that these mechanisms are happening. So here's our transition state 1, our transition state 2, via the 2 different mechanisms. Here's what the intermediate is. And I want to say that I misspoke either yesterday or the day before when I said that we can't see the intermediates. In some cases, we can. We can use pretty advanced spectroscopic techniques, and we'll be learning a little bit about spectroscopy later, to isolate intermediates in some cases. They most of the time don't stick around for very long, but we can, in some cases, isolate an intermediate and be able to say, yes, this is actually one of the products of one of the steps in this reaction. But it's hard, so we don't, it doesn't happen all the time. What we definitely cannot see or isolate is the transition states. That's what is absolutely theoretical, and we can only disprove them. We cannot prove that that is, in fact, the way things work. So being able to, this is a great way to set up a study, an experimental study, because you're not saying, is it bimolecular, is it trimolecular? You're saying, which of these two theories matches what we see when we do these experiments, okay? And you'll see they also have a potential energy diagram, and you will notice that in these potential energy diagrams, our intermediates are in fact lower in energy than our reactants, and you do see that sometimes. You'll see that it also looks like this one is lower than the products, but the idea is the product goes into a different state as soon as it's formed, so that the actual product is lower. So you do sometimes see, again, in more sophisticated reactions and experiments, you can see a transition state, or an intermediate that is lower than the reactants, but not lower than the products. So you're not going to need to do anything like this for IB Chem, but if you were to say go into chemistry, this might be the kind of thing that you would do with a little bit of differential equations and some other stuff. Okay, so that's this, but this kind of thing is why we care about reaction rates and all of these things that I'm going to teach you that look like it's just some sort of mathematical trick to study this. And hopefully we'll be able to take some of your data from the kinetics lab, and certainly we can take some other sample data as well to show how this would play out in a lab setting, even here, even, for example, in an IA that you might do. So this is why we want to make wastewater treatment more effective and more efficient. We need to know what the rate equations are. So page 7 starts talking about these rate equations or rate laws. So rate law is what you might see in some cases, or rate expression, rate law. All of these are interchangeable. And this is basically a way to describe the effects of concentration changes of our reactants. How much of an effect does each reactant have, the concentration of each reactant have on the rate of the overall rate of the reaction? So if we increase the concentration of one reactant versus another, does that have a bigger or smaller effect on the rate? That's what we're trying to do here. And so the rate equation is written as a constant K, which we'll talk about in a bit, times the concentration. Remember that square brackets equals concentration specifically in moles per dm3. Okay. So moles per liter, or molarity, or big M, those are all the same thing, what is represented by something in square brackets. And so the thing in square brackets is going to be a substance. It's going to be, in this case, one of the reactants. Note that we don't care about the products, because what we're interested in is how do we make the reaction go faster or slower. And so it's going to in this case, until we get to the next unit, it's going to depend just on the reaction concentrations. And then we're going to take those concentrations and raise them to a particular power. Could be 1, 2, 3. We're not going to go beyond that. And those are what we call orders of reaction. The order of reaction has to do with the relative effect of that concentration of that reactant on the overall rate of the reaction. When we add those two exponents together, that gives us the overall order of the reaction. This we can do if we have an elementary reaction, if we have a one-step reaction. Okay, we can calculate it. If we know that it's just one step, we can calculate it based on the concentrations of A and B, as long as we know the order of reaction. Okay. We're going to talk about them in a second, but it's basically, if you think about it, it's how much of an effect is changing this concentration going to have on the rate. Right, because if we're raising it to the first power, then it's just, that concentration. If we're raising it to the third power, that's going to have a much bigger effect on the rate. Okay. For multi-step reactions, we actually can't use this because there are multiple steps, and we have to actually use experimental results, like they did in the wastewater paper. Okay. So you're going to learn how to write a rate equation for a elementary reaction, and then we're going to talk about how to use data to determine the rate equation for a given reaction. So orders of reaction, again, this is the power to which the concentration is raised. Even in an elementary reaction, we cannot tell what those numbers are, what x and y are, what those exponents are, without looking at some experimental data. We use experimental data to determine what those exponents must be. And then later we'll be able to solve for the reaction constant, the rate constant. Generally, we're going to have zero order, first order, or second order. We're not even actually in this class going to get to anything higher than that, and most reactions are going to be one of those three. Okay. In a zero order reaction, then, or a zero order with respect to one of the reactants, that means that changing the concentration has absolutely no effect on the rate of the reaction. We could double the concentration and it wouldn't matter. Okay, that's obviously not going to happen in a unimolecular reaction because that wouldn't make any sense. If we only have one reactant, then changing the concentration is in fact going to change the rate. But if we have multiple reactants, sometimes one of those reactants actually doesn't affect the rate. It's the other reactant that determines the rate. First order is going to be with a exponent being 1, and it's a direct proportionality. As we increase the concentration, the reaction rate will increase. Second order, if it's a squared instead of to the power of 1 or to the power of 0, then that's going to increase the rate according to the square of the change of the concentration. Okay, so zero order, first order, second order. That, again, is going to be the number of the exponent. Here we can see in this table, which I think is the bottom of the page, what this kind of more intuitive way of looking at this. Okay, so if we were to double, triple, or quadruple the change in the concentration of a particular reactant, if the reaction is zero order with respect to that, there's going to be no change in the rate. Okay, we could double it, we could triple it, we could quintuple it. Won't matter. Reaction's still going to have the same rate. First order, we're going to see if we double the concentration, we double the rate. If we triple the concentration, we triple the rate. So that's that direct relationship between concentration and rate that we see in a first order reaction, which is where our exponent is going to be 1. Change in a second order reaction with respect to that reactant. If we double the concentration, we're going to quadruple, all right, because we've got that power of 2 up there. If we triple it, it's going to be multiplied by 9. If we quadruple it, it's going to be multiplied by 16. So you're basically taking this and squaring it, right? So. And again, we're only going to go up to second order, and I don't think you're going to. You're definitely not going to see anything higher than quadrupled most of the time. you're going to see doubled or tripled in exercises that you might need to do. So again, this is going to be that's a to the 0, which is equal to 1, right? A to the first is equal to a, and then this is going to be a squared. Okay. And again, this is with respect to a particular reactant. So if you have more than one reactant, you can have an equation that is 0 order with respect to one of the reactants, second order with respect to the other, or first order with respect to both. All right, and that's something that we have to experimentally determine. Okay, so how do we do that? This is where we look at initial rates of reaction. Remember that from the last part of this unit, the initial rate is what we can measure by taking the tangent line of the slope of the curve at the beginning of the reaction. And so we can determine the initial rate of the reaction, and we can use those rates. We can measure those rates under different circumstances with different concentrations of our reactants. In this case, excuse me. In this case, this is the reaction that we're looking at in the example. Is this, what is the molecularity of this reaction? Yeah. It's bimolecular. Yep. We've got NO and we've got O2. So we've got two different reactions, or reactants, excuse me. And the person studying this reaction does the reaction under 3 different conditions. Okay? It's always got to be at least 3, because we need to have a baseline, okay? And then we need to have one where we change one of the reactants but not the other. And then we need to have a third one where we change the other reactant but not the first one. Okay? Because otherwise, if we change 2 things at once, we can't tell what the effect of those changes were. But if we just change one thing at a time, that's science. Okay? So you can see in these example data that we have initial reaction or initial concentrations, both of them at 0.01. They don't have to be the same. Okay. They don't have to be the same in the baseline experiment. Okay. In some cases they will be. All right. And we have a rate of reaction that we have measured by charting the course of the either production of the product or disappearance of the reactants or whatever it is that we're measuring. And we have calculated an initial rate of reaction. So we have a baseline rate. And then if we double, so you can see that in this version we have doubled, let me rewrite that, times 2. Okay, we've doubled the concentration of NO. What effect does that have on the rate? How much faster is the rate in experiment 2 versus the rate in experiment 1? And you might initially, for a moment, look at this and say, it's not faster, it's 1 versus 2.5. This one's faster. But no, pay attention to the exponents in the scientific notation. Rates are almost always going to be shown in scientific notation, okay, in these kinds of problems. So what is the relationship between 2.5 times 10 to the negative 5th and 1.0 times 10 to the negative 4th? Luke. Yep, so this is 4 times faster. If you don't have that intuitive grasp of the exponents and the scientific notation, you can plug this into your calculator and say 1.0 times 10 to the negative 4th divided by 2.5 times 10 to the negative 5th, and this is what you will get. Okay, so you don't have to be able to do that in your head. If you can, it's faster. So the more practice you have with that, the better. But it's not like you can't do it if you can't figure that out in your head. All right, so that's 1 versus 2. Now we want to look at not 2 versus 3, because we're changing both of those things between experiment 2 and experiment 3. We want to look at 1 versus 3, because in this one, we're keeping the NO the same, and we are doubling the O2. Okay. And you may have examples, you will have examples that might have 3 things, or might have other versions of this. This is the simplest version, where we double one concentration, then we double the other concentration, and we get the rates. But it can be more complicated, so you have to really think about, okay, which 2 experiments am I comparing to get any particular relationship? Okay. So in this one, we're comparing experiment 1 versus experiment 2. Here for the O2, we're comparing experiment 1 versus experiment 3. So now we've got 5 times 10 to the negative 5th instead of 2.5 times 10 to the negative 5th. So what is the relationship there? How much have we increased the rate? By 2, yeah. So this is times 2, and the rate is changed by 2. Okay, by twice. Okay. So then we can say, what's the order of reaction for each reactant? So if when we double it, we get quadruple, what is the order with respect to NO? 0, 1, or 2? Actually, it's probably on there, isn't it? On the example? Yeah. Okay. So this is, sorry, I forgot that this was a fully done example. So this is, because this is a square, that means that NO is second order. Okay. We double O2, then we double the reaction rate, so that's going to be first order. Okay. So we're doubling and doubling. That's first order. Okay, so now we can write a rate equation where we can put the appropriate coefficients. So we can say that the rate is equal to K, which is the rate constant. We'll talk more about that later. We'll talk about it a little bit in a second, but more about it tomorrow. Rate constant times the concentration of NO squared times the concentration of O2. So both of them are contributing to possible changes in the rate. Nobody is zero order. But the NO, changing the concentration of NO is going to change the rate more than changing the concentration of O2. Okay? And again, this is not something that we know that we can predict without doing the experiments. Okay? And then the overall order of the reaction, don't forget that if you see this in a rate equation, right, this is, that there's a 1 there, okay, because it's first order. So we don't generally write, that's one of the many invisible ones in chemistry, just like we don't write every subscript if it's a 1 or every coefficient if it's 1. We also don't write exponents if they're 1. But don't forget that that is a 1. If it was zero order, it would not be in the rate equation at all, okay? Because that would, something raised to the 0th power is just the number 1. So we put it in the expression, okay? So when we're looking at the overall reaction order, then we add these up, 2 plus 1. So this is third order overall. It is first order with respect to oxygen. It is second order with respect to NO. It is third order overall. Okay. Now what's cool about this is we have all this rate data. So because we have these rate data and now we have the expression, we can solve for K. And we can find out what the rate constant is under these conditions. So the way we would do that is, and I made myself a whole board here, but I actually need the numbers here. We're just going to take one of the experiments, and it doesn't matter which one, because K is a constant. So it doesn't matter what the concentrations are of those two things. If we have the concentrations and we have the rate of reaction, then we can solve for K. And it's going to be, you should be able to do it for each of these and come up with the same answer. Okay, so you just pick one and solve it. So we've got 0.01, 0.01, 2.5 times 10 to the negative fifth. So we know that our rate, I'm just going to rewrite the equation. Okay. Now we know I'm going to pick experiment 1. The rate is 2.5 times 10 to the negative fifth. Is equal to K times 0.01 squared times 0.01. So it's really 0.01 cubed, but when you put it all together, okay? So we can then solve for K by taking this whole thing and dividing both sides by that, right? So K is going to be equal to 2.5 times 10 to the negative fifth over 0.01 cubed. Okay. And you can plug that into your calculator and get that, get a number for K. Okay. So I haven't done this in a bit, so I don't have it at the tip of my fingers. So 2.5 is 10 negative fifth divided by, where is it? I gotta figure out how to do that. How was that? Oh, wait. Always make sure that if you've got an operation in the denominator that you use parentheses when you're entering it into your calculator. Otherwise, you're going to get something that is incorrect. And this is one that, you know, if you're good with exponents and powers of 10, you could probably do in your head, but I am not that quick with that, so hence calculator. Tell me if you get a number different from mine if you were punching it in. But assuming I didn't screw that up, then we can plop that in to our rate equation, and we can say that the rate is equal to 25 times squared times 2. All right. Yes?
Would there be any units attached?
That's a great question. No, there are no units for the rate constant. Well, no, I'm sorry. No. I apologize. I'm thinking of something else. No, there are units for the rate constant, and we're going to talk about that. Did I add this? Yeah. We're going to talk about that tomorrow because we'll do more with K. But yeah, finding the units of the rate constant, you can. Actually, you know what? We've only got 5 minutes left. Let's figure it out. Okay? I'm going to duplicate this so that I can erase some stuff. Oops. Okay, so we can use our, right, yeah, that was a duplicate. We can use, notice in this table, the units are given for each column. This is how you should report data. When you are reporting data in a table. The units, and also if you have them, uncertainties, should be in the header. Okay, so that everyone can see that, it's 2.5 times 10 to the negative fifth moles per decimeter cubed per second. That's the rate. Okay, concentration divided by time, that's how we get the rate, right? Y over X. And then we have moles per decimeter cubed as our concentrations. So in this case, we are going to have, let's see, so we've got moles per decimeter cubed per second. Okay. And then we've got moles per decimeter cubed squared and moles per decimeter cubed. If you need to figure out units, this is how you do it. You treat the units the same way that you treated the numbers. Okay? So you plug in whatever the units are of the things that you know, and then you treat them the same way you would treat the numbers. So let me get rid of this and say, instead of what the numbers are, let's figure out the units. So we've got moles, decimeter, -3, seconds to -1. Okay. And on the bottom, we've got moles, essentially, sorry, that should be negative. We've got moles per decimeter cubed, all cubed, right? That's a negative. I keep doing that. I apologize. Should add one to my piggy bank. This is me struggling with IB units, piggy bank. Whatever that ends up with at the end of the year is how much money we have to spend on a party. Okay, so this is where knowing how to use fractions and exponents comes in really handy. Okay, what do we do when we have an exponent raised to an exponent? Yeah. No, we multiply them. Okay, so this is going to become moles cubed decimeters to the -9th. Yeah. No, I mean, I have to think about it every time, honestly, because we don't do this very often. This is one of the few times in this course that you'll have to remember how to do that. Okay. All right, so what do we do now with moles on top and moles cubed on the bottom? What do we do when we're dividing exponents? That's when we're going to subtract, yeah. So multiplying exponents, you add. Dividing exponents, you subtract. Power of multiplies. So we've got moles to the first divided by moles to the third. That's going to be moles to the -2. Right? That makes sense? 1 minus 3. We've got dm to the -3rd minus dm to the -9th. Okay? So -3 minus -9 gives us what? 6. Okay. And then we're going to have seconds to the -1. Okay? So this is, again, this might be 1 point on a question on the exam, but they expect that you'll know how to do this. And we'll talk more about this later, and you'll get some practice problems with this. Okay? And so the units for K are going to be different for every equation, or every order of reaction. Different orders of reaction are going to have different units of K. So we'll talk about that more tomorrow.